Good morning. The presentation is in English or you speak French? English? Okay. This presentation, we try to present you an approach of AI, process, AI function, and actually concerning the smart digital sensing for nuclear industry. My colleague and me present you this presentation in two different parts. The first part is essentially concerning the instrumentation and sensor. The context of AI is very specific. Yes. AI is referred to a collection of new technology. Oh. Ça disparaît à chaque fois.
Vous pouvez le faire directement sur l'ordinateur? Vous pouvez le faire directement sur l'ordinateur? Ouais, avec les trucs italiens. Le câble.
Excuse me. Ah, okay. Restart. Now concerning EA. EA processor or EA function. EA is referred to a collection of new technology that combine numerical data, process algorithms, and continuously increasing computing power to develop systems with a capacity of resolving complex situations in a way of similar to a human logic and reasoning. Concerning the field of nuclear instrumentation, it's very specific because the field of nuclear instrumentation it requires a great deal of experimental and theoretical activity. EA-based method actually offer opportunity to accelerate different topics. It could be accelerate the decision making, the analysis of information, extracting for simulation and experimental data. If you look on this slide is concerning the measurements data for AI, and you can see the different goal or different also sensor or different topics. This means that we have actually the possibility to use AI in a sensor and instrumentation ecosystem. For example, in chemistry, for the scintillator, plastic scintillator, in sensor, in electronics parts, you can embed it of some software inside, metrology, physics model and simulation, which is very important. And after the presentation, you have some discussion if you want. Signal processing, but this part is also including in the electronics part. Advancing AI, and also one thing which is very important is the part of the cybersecurity or cyberphysics security. This slide is just an explanation from the physical phenomenon to the advancing measurements products. You can see that you can use the AI process or AI function in different steps of the development of a new system measurement. For the first step, it's concerning the numerical sensor design. The second step concerning the physics-oriented sensor development and prototyping, in which you can accelerate the prototyping of the systems. The sensor qualification, it's also one step which is very important. And after that, you can have the sensor system prototyping, and then beyond the measurement, the AI function that you can including directly in the software, which is embedded directly in the sensor or in our computer. And the last step, just before the production, is concerning the robust, secure, and adaptive sensor deployment. Next, we can just present you just two platforms that we developed since 2012. And the first platform is to present you the workflow of the data from the sensor directly to the software and to the decision. Actually, in this platform, you have different parts, for several parts. The first part is concerning directly the sensor. It's developing in order to have the whole information. And the first part for the sensor is typically the management, the driver part of the software, the API of the software. And then you have the data. This means that we have the opportunity and we have also the different aspect to include directly in the data the whole information that we need to perform the use of the data from the sensor. The next step is the processing. This means that we're including in a specific class the whole function to do the different analysis with the sensor. And then the last one is the user interface concerning the information, Nuclide identification, for example, or component identification. This platform is completely generic, and actually, one thing which is important to know, that for each sensor, we have one class. And this class, you have different other API in order to use completely the whole function of a sensor on the whole data of a sensor. And we have also one thing which is very important, is that we can use this platform not only for Windows, but you can use for Linux, or you can use also for the smartphone or other different support. Two examples in which we use this platform. The first one is concerning the gamma imager. And in this gamma imager, we're including the different parts of this platform. The second one is concerning the portal monitors that we use for the security topics. This slide is not only the key feature in order to have an idea, but every year we have some project in order to perform this platform. The second platform is concerning the Expressif platform. Expressif platform, fast automatic reasoning for decision support. This platform is based on an inference engine in which you can include directly the data in from the sensor, the contextual logs, text or image, and you also use the knowledge base. This knowledge base is come from an expert, and you can directly include the expert information in these tools in order to perform the decision. Leveraging real time, multiple type input. This means you can make a fusion between the knowledge of an expert and a database from the internet, for example, or from the text, or from another database. By modeling human knowledge with the fuzzy logic rules. And to make these fuzzy logic rules is very simple. And one thing which is very important is that the decision from this platform can be supported by explanations and thus audited. And in this case, it's very important to know this aspect. Two examples. The first one is concerning an European project of security in order to detect or to have a decision concerning detection of different components. Concerning the input data, we use 28 components and seven examples per component. And the output is concerning the detection and classification of a different substance. The other one is the predicting materials properties from process parameters. This means that you use, in this case, two different experts. The first one, in order to put the raw materials and the different set of the parameters to build up these materials, and the other one, expert, is concerning the observation. And in this case, you can make a fusion between both in order to have a decision and to perform the creation of this type of materials. The key feature is concerning the robustness in regards to problem inputs, interpretability and explainability of decision. Rules are written in an almost natural language and was easily interpreted. This means that you have a user interface, very simple to use, and you just put the rules in a standard language, like if this, then that. And you can put every rules. And one thing which is very important is concerning the number of the rules that you can execute per second. Actually, you can use 1 million rules per second. And this means that you can have a flow and throw data directly in your systems and have a decision directly in real time. This is concerning the key feature of these tools. And then the next step that we have is the mixed and the link between the two previous platform, the PACT and Expressif. And this means that we have an hybrid tools in order to have directly the flow data from the sensor directly to the decision software. This slide is very to illustrate some development that we have actually used this type of platforms. And then, in order to because the time is go. The next part of the presentation is concerning the EA requirements for nuclear industry versus regulation and certification. Eric.
Thank you, Karim. So to see this point, we start by making a focus on the activity on spectral analysis software, which is a huge activity for many years now. And in the early stages of this software development, there were a lot of restrictions on the spectra, on the detectors, on the resolution of detectors, and for example, of a Nuclide dataset that we can use. And more with years, people tend to increase the flexibility of this software, for example, to relax the spectral complexity, to relax also the type of detectors we can use, and to relax the resolution. And more, automating this software is a target for developers. And for example, this software called Magix now let the user just specify few parameters like minimum energy, maximum, and a rule for energy resolution. But still, this process of spectral analysis is an expert-driven process. So what would be the next step? The next step in this area should be, in fact, to see, for example, identification of Nuclide as a machine learning problem. And in this case, we try to mitigate the role of a human intervention in this software and also the use of nuclear databases. And here you see that the problem is encountered in the field of machine learning. This means that we use a database of spectra, and we make statistical prediction to identify the nuclide in an experimental spectrum. So in this case, a big problem which appears naturally is the more and more we use black boxes in the identification process, we need to be confident in the results of the algorithm. So there is a special need in nuclear sciences, in nuclear industry, for trustworthy AI. And this problem has been pointed out quite recently, but regulatory authorities see and ask the question of, well, there are a lot of systems now, devices which embed machine learning algorithm inside. And so what should we do? What can we expect and what should we observe to agree with the use of this algorithm in nuclear devices? And this we can see easily for obvious safety reasons that the more the device is high risk, the more machine learning algorithms have to obey to some rules, to some certifications, and which are listed here. And for example, we have to be able to quantify uncertainty. Systems have to be resilient and robustness and so on. And this is a very challenge for developing a machine learning-based solution now in nuclear sciences. Another point, and we will conclude on this point, is the use of AI to enhance simulation, and in fact also to use simulation to enhance AI. So we can just say that, well, simulations in nuclear engineering is ubiquitous. For example, when we want to design detector, when we model scene or process and so on. And simulation is always a forward simulation. We take some parameters at the input of simulations, and we get observables. And there is something which is quite particular to nuclear sciences. We have a lot of random phenomena because of the physics, of radiation physics involved in this field. So simulations are quite cost expensive in this area, and this computational burden is a kind of limit to the use of simulation in this field. So what we can expect with the use of AI in simulation is, for example, the building of meta models, which leads to a huge use acceleration of the simulation process. We can build database with simulations, which can be used, for example, in the Nuclide process identification, and we can enhance database also with AI. So this is a very wide and active area. And just for the conclusion now, we explore one point which is related to simulation, but what we can call the inverse problem. In fact, if simulation goes from the parameters to observables, how to go from observables to feature? When we want to design a detector or to model a scene, this is the question we have. And to do this, the expertise of human is more or less to use a try and error process, which is terribly dull. At the best, we can use a screening process, but in both situations, it's extremely difficult to ensure that the solution we get are reliable or we can trust them. Okay. So the question we ask for here is how to get this reliability of the solution, because, well, nuclear engineering needs this reliability on parameters. So we are going to show a case study, for example. Just on the right, we have a germanium detector, but with some unknowns inside, so the geometry, dead layers, and so on. So can we estimate the absolute efficiency of a detector using AI models? So this is how we can see this problem. Well, now we are going to speak about what is, in fact, simulation-based inference enhanced by AI. Well, as I said before, stochastic simulation, which is used in nuclear sciences, in fact, is a random generator. We sample energies. So what we want to do here is to characterize the solution that we are going to estimate, the parameters of the scene, of the detectors, and so on, with some distribution, with some probabilistic rules. And this statistical characterization is very difficult when we use simulation, and for this, we are going to estimate a surrogate of a simulator based on what we call deep learning generative models. And with this introduction of AI in the process, we can quantify uncertainty, which is the answer to the probabilistic assessment requirement for trustworthy AI. We can try to fill the gap between simulation and reality, which is more or less always a very huge problem when people want to use simulation in this area. And finally, we try to explore the space of the parameters of the scene with an adaptive strategy, which is called active learning. And okay, sorry. So this is how the process works. We can make simulations, use and build a database of simulations using simulation software like MCNP, for example. On the other hand, we have some observations, some data, and we want to make inference from the data. And then, thanks to generative models, we can combine simulation and inference to get some parameters of the geometry. And we get some parameters, but just not one value. Thanks to this approach, for example, we can have all the distributions of the parameters. So we improve the reliability of the estimator and of the approach. So this is what I wanted to say for this part, and I think that we can now conclude. Thank you for your attention.
And now, if you have some question, because we have no time, you can come directly to the booth of the CEA, and in this case, we can continue the discussion if you want. Thank you.